We're gonna start back from spring break with the next part of our crypto unit, which is block and stream ciphers. I'm Sagnik, and we're gonna dive right into it. So a couple of announcements. This weekend, starting from tomorrow, we're gonna have a tracer fire going on. So we'd like to see you there this weekend. The Sandia Q&A is going to be tomorrow from 6:30 to 8 p.m. And there's going to be an event on March 23rd to 24th from 9 a.m. to 5 p.m., 9 a.m. to 3 p.m. respectively. So go to those two events and make yourselves known. And you could register down at the SIGPwny link. So yeah, that link right over there. The next Sunday, we're gonna have a PhD student come, Max Bland, and he's gonna talk about kernel pwn, Linux kernel exploitation. So if you're interested in that, I'd highly suggest coming. So yeah, let's dive right into it. So here's the meeting flag. Couple of seconds. And yeah, pretty accurate XKCD, I'd say.
This is an actual XKCD?
Yeah, they actually explain
No, but like,
encryption.
is this from XKCD?
Yeah.
Where's the joke?
So it's more of a,
What's wrong with this left hand?
I guess it's a statement. It is the statement of all time.
Joke is
The joke is, chat, is this real?
no, the joke is decrypting means doing everything in reverse. How's that a joke?
It's not, I mean,
I mean,
it's not always true.
Encryption go bird.
All right. So we're gonna start off the stream cipher and block ciphers unit by talking a little bit about pseudo-randomness. So we specifically say a sequence of symbols is pseudo-random if it seems to look completely random, yet it's actually been made by a deterministic process. So it's completely repeatable every time you give it the same seed. So it's actually provably impossible that you're able to take a short random string and turn it into a long, truly random string. And in order to actually like make the lengthening transformation, you need to go through what we call a pseudo-random generator. So pseudo-random generators are used to make a short string turn into a long string that looks random. So being a little more formal here, a PRG, or a pseudo-random generator G, is any kind of mapping from n bits to something longer, like n plus s bits. So it makes it very hard for what we call any polynomial time guesser to actually guess the output of the PRG given the input strings. So guessers cannot tell it apart from the output of a truly random function within a reasonable time span. It's very hard for them. So formally, for all probabilistic polynomial time adversaries, the probability that the adversary actually like detects and properly guesses the random string that'll output given the seed k, and the difference between guessing it from a truly random function is negligible. So yeah, a bit of terminology there. Shouldn't be too hard.
Equals one notation.
So an adversary will return 1 if it's able to correctly guess that whatever the output will be given like the seed k, without actually having access to the internals of the actual PRG. So it only has like Oracle access, what we say. So we're able to like pass stuff into G, but we don't have any idea about what the actual internals are. So without that, like with that black box knowledge, are we able to like properly guess what the random output will be? And like the probability of us actually like hitting that guess correctly is very low. So something that could be negligible is something like 1/2 to the power of n. So that's a very rare chance for it to happen if n is sufficiently large. Yeah. Does everyone get that? Right. So do we have security? The unfortunate answer is because a PRG is not truly random and is deterministic, it's not actually as secure as if you were to have like something that's truly random, but we could get reasonable enough. And in order to build on top of that pseudo randomness, we're able to introduce probabilistic encryption. So the idea is that encrypting the same plain text multiple times, each time will give a different ciphertext. Now, from a base PRG, that isn't inherently possible because a PRG is deterministic. If I give my name, which is Sagnik, to the PRG, it'll output some random string. But if I give that name again into the PRG, it's going to output the same string. And we don't necessarily want that to happen. So the idea is that we're going to seed it with another random variable R with the rest of the encryption process. So some random R is chosen differently every time we call encryption on the key. And the receiver who gets like R as a result of this, of course, we can't like give R out to just anybody. It has to be the receiver. The receiver who gets R can then decrypt it. And then what they have to do is immediately drop R. And we're going to get to why in a little bit of a second. Yeah.
So R is like the initialization vector from AES, right?
Yes, IV.
And is it insecure to go past that publicly if the key isn't known?
Well,
Otherwise, how do you sync it up?
wait, I'm not sure if I entirely follow.
Yeah, so if I were to send someone an encrypted blob, right, in AES, would I have to give them the IV as well for it to get synced up, or is that considered a bad practice?
Well, the IV is going to be still like known to them, but we're
Okay.
gonna like strip the IV. The bad thing is what happens when that same IV gets used again in
Okay.
another. So essentially, you could treat it kind of like a nonce or a number used only once.
Okay.
But it's okay if the receiver knows the IV for that specific scenario.
Okay.
Yeah. Anyone else? All right. So we're now here towards the stream cipher. So a stream cipher is such a probabilistic encryption that builds on top of the PRGs we just talked about. And the cryptographic key and algorithm are applied to each binary digit as a sort of input. So that input is treated as a data stream. So the key is what's actually being inputted into the PRG, and the output, like lengthened random bits of info, is what we call the key stream. So a general example of a stream cipher I just cooked up. Not sure if it's entirely secure or not. Maybe you could prove it. Let's say we calculate some key stream with a random IV, which is the IV, the R we were talking about before. So this is G of IV and K. So that's going to give us some random key stream, right? So then we encrypt the message at the byte level. You could also do the bit level. They're bit-based stream ciphers, but most of the ones we work with are at the single byte level. So then we encrypt the message M, which is like treated as a data stream of length n plus s, and we calculate C, which gives us the IV that we have, and the key stream XORed with them for each byte level. So this encryption actually happens byte by byte is an important part to consider when talking about the stream cipher. And the decryption we do is very similar. Byte by byte level, we just do kind of everything in reverse, like the comic said. We have the key stream and we XOR it with the ciphertext. And because XOR is commutative, we'll lead back to the plain text bits, and we discard the IV at the end. So this is a kind of example of like how a stream cipher would be implemented. So yeah, just know it's at the byte level. So the idea behind the stream cipher is we want to make it difficult for cryptanalysis to be done. If we make like the stuff happen on like larger and larger blocks, foreshadowing, if we make the stream cipher encrypt on larger blocks, it might be, depending on how the cipher is implemented, it might make it very easy to like check for patterns within the input data and the output data. So we want to make it very difficult by only doing it at the byte level so that each pattern is specific only to the byte. So cryptanalysis is very hard for stream ciphers. And longer pseudo randomly generated key streams will make it also very resistant to brute force. Because if I need to actually brute force the encryption, that's equivalent to reconstructing the key. But what happens if the key stream is really, really long? Then it will be very, very hard to actually get the original output. So since we call the algorithm on a smaller space of input, it requires fewer lines of code and thus takes up less power compared to implementing a block cipher. So a lot of stream ciphers encrypt and decrypt really, really fast, especially like some of the modern ones. So a lot of new encryption standards nowadays use stream ciphers to encrypt and send data because it would be a lot faster and more efficient than some other protocols like RSA, which takes up a lot more power depending on like how big the RSA byte is. Like 4096 takes up a lot of power, for instance, but I could have less power if I use a stream cipher. Yeah. So a couple of examples of commonly used stream ciphers are SIGPwny, Cha-Cha Real Smooth. So this is a very popular used low power stream cipher that's pretty secure. one that's not so secure is the reversed RC4, which is an example of an insecure stream cipher, especially when you don't discard the beginning of the key stream. I'm going to ask you why that is in the next slide. We got a couple of more that aren't talked about as much, but I just decided to list them there. So more on RC4. This is the general algorithm that we use. So the key schedule just kind of uses the output from the PRG that we listed in order to generate the key stream. And then we kind of like swap and create the output from that. So what do you think looks off just looking at these two algorithms? What do you think might be an issue with RC4?
You just do the loop in reverse.
Well, I mean, that would decrypt it. That's how you would like get that. But there might be a little more of something. If you guys are familiar with RC4, feel free to speak up. Because there's a very well-known attack because of the field they use.
Use the key multiple times over, or am I misreading that?
I mean, that would be a bad issue in general for any stream cipher, because then it just becomes like a repeated key. Kind of like what happens if you use like OTP's password more than once. So yes.
What exactly is the key schedule doing?
Right. So it's generating the key stream based on the output from the PRG. That's what the, yeah. So there's a way to actually regenerate parts of the key based on a couple of patterns that happen as a result of the first few bytes of output. So the key schedule is insufficient because the second byte in particular is extremely biased towards returning 0 if the first byte is not 0, which is a little weird to see from just this general code. But the idea is that because there's like this pattern that happens based on the key stream just simply doing a swap and simple mod operation, there exist patterns in the actual resulting key stream that might not be good. So there is a really famous protocol that was recently used called WEP that used those first few bytes in the key stream from RC4. And as a result, because people were able to see that pattern, the key stream was able to be recovered, which is not good in the right hands. So that's a big weakness in RC4. So we consider it generally insecure. Anyways, going back to the multiple time use, one of the weaknesses in stream ciphers is that it can be vulnerable to a 2-time pad. And if the key stream is used more than once, and you have like messages A of B with equal length, and you just take the XOR operations, you can see it kind of runs into the same problem as the 1-time pad. If you have like the 2 encryptions and XOR them, it will reveal patterns about the original plain text, because encryption of A XORed with encryption of B will be equal to A XORed with B. So there's a big pattern. And if you have sufficiently enough plain text, you could do what we call a crib dragging attack. So never use the same key more than once. General good practice in this space. It's also very easy to do a bit flip attack, which is when you change like 1 bit in the ciphertext. That also affects block ciphers. So I'm going to talk a bit more about that attack later. And the final one is a chosen IV attack, which if you choose particular values for the IV, such as like you make the IVs all nulls, then the resulting key stream can reveal extra patterns and extra bits in the key stream that might not be entirely random. And this might weaken the key and make the random bits less, which means the effective key length is now shortened, which you don't want to do, because if your PRG returns a smaller random value, that kind of defeats the purpose. So this might weaken the key and follow up with weak key attacks. So just be aware of those when you see stream cipher problems, that these are some common things that you could do. So we're going to move on to block ciphers now. And this is another type of deterministic encryption that builds on pseudo-randomness similar to the stream cipher, except instead of operating at the byte or bit level, we take a look at entire blocks of text now. So that would be typically 16 or 32 bytes, which is the word level would be the 32 bytes, and the block level would be 16. So instead of treating it as a continuous stream of byte data, we take a look at each block in deterministically encrypt it in a similar fashion. So the algorithm is used to transform each block into some garbled text, and then the results of each block's ciphertext is then combined together to give us the full output. At least the normal block cipher is. There's a couple of modes which I'll talk about later. So the most famous one you probably all know of is AES encryption, and that's a block cipher that operates on a fixed block length of 16 bytes or 128 bits. So there's a total of 3 different bit lengths other than 128 for the keys, which are AES 128, 256, and 192, and they increase in security because of the key length being longer. But for the purposes of simplicity and the widespread use, we'll consider AES every time I talk about it to be 128 bits. So the same ideas that we're going to talk about also extend to the higher key dimensions. So encryption for 128 consists of 10 rounds of encryption, 192 is 12 rounds, and 256 is 14 rounds. And these are specifically numbers chosen by Rindale, who made the standard. So there's mainly 4 main steps to the AES encryption that I'll kind of skirt over. But because this actually constituted a really, really long meeting last year, I'm just going to briefly talk about them. If you really want to see the inner math, I'd highly suggest checking out 2023's meeting. But anyways, the main steps are the subbytes, which uses like a global lookup table to substitute a set of bits in the current block in a random order. The shift rows will shift the rows of the current block by kind of doing like a vertical shift operation. The mixed columns will do a map mul. So shift rows and mixed columns, a very important thing to note is that they're both linear. And the add round key will perform the bitwise XOR operations, which is an affine transformation. This is kind of a bit of like the inner workings of AES, but just know that the output is pseudo-random as a result. And because it's also efficiently invertible, we say that AES itself is a pseudo-random permutation, which is a pseudo-random generator, but efficiently reversible, because each of these steps could be reversed. Any questions? Because there's kind of a lot.
So if each step can be efficiently reversed, why is it still secure?
Right, and that's because the inverse of all of these depends entirely on whether or not the key is known, which is true for any symmetric cipher, right? However, if the attacker doesn't have access to the key, then he will need to reconstruct the key from these given steps, which might not be that easy considering the fact that all of these work together to create like a non-linear transformation. But it kind of depends on what's known and what's not known to any given person. If the right people know like the right steps to actually take, then it's very easy. But if you're given like a new frame and you don't know how you got to there, it might be very hard to like retrace your steps back. And that hardness is where the security comes from. So yeah. This is all efficient given that you know the key. Consider that. Okay, so I'm going to talk mainly about modes right now. So block ciphers like AES often work on different modes of encryption that governs how each block is encrypted. And the algorithm itself is only good enough to decrypt one block. In the case of AES, that's 16 bytes of data. And we need to make modes in order to like figure out how to like encrypt bigger blocks of data by separating it into multiple blocks. So the main ones that we use in the industry for AES are electronic codebook, which is the individually encrypt each block style. It's not very secure, as you'll see very soon. There's a output feedback, which is kind of like AES turned into a stream cipher, which I'll show that diagram as well. There's counter mode, cipher blockchaining mode, and cipher feedback mode, which is also a stream style cipher. So this is the diagram for ECB. Each block is independently encrypted of the rest. Does anyone know why this might be a problem? Because ECB is not secure.
So in this example, the plain text is split up into separate blocks?
Yes. So each one is of length 16 bytes and they're all independently encrypted. Yeah.
Does this become kind of like a substitution cipher if you do enough plain text? No.
Well, a very, very large amount of plain text. Specifically, I think it was 2 to the 64 plain text. So that's fairly large number. But yes, eventually it does kind of condense down into that. There does exist an attack, but that's not entirely why. Yes.
Maybe because like you're using the key each time, so.
I mean, that's something, but that won't really be like that much of a problem. The problem happens when you take way more different plain text sections and use the same key, like specifically 2 to the 64 of them. So that's not that bad. Yes.
Yeah, the same plain text block, the same text block, the same position.
Yes, that is indeed a big problem. So I'm going to show the diagram at the very end, but that does actually provide a big problem, especially when you take a look at like images encrypted with ECB. So cipher modes, this is a bit of a different one, which is CBC mode. So this time, instead of simply encrypting each block independently of the next one, we chain the previous block of encryption and feed it into the next one and XOR it with the plain text. So this actually makes sure that none of the, if you just take each block separately and decrypt them, you can't really see any difference in like the output versus the input. So you can't really see entire patterns because they're all kind of chained together in a way. But this is a little more secure than ECB. These are the two stream modes, which if you could see here, the key and the IV kind of also get fed into the encryption. Oh,
Question previously.
yeah.
So would you really should just break it into text into the sections to block cipher?
In a way, yeah. So again, like any block cipher, you'll always like divide the plain text into like the block size. For AES, this is 16 bytes, right? So regardless of the actual size of the plain text, which is like all three of those blocks, let's consider, you're going to separate that plain text into like the blocks and then pad them to get to 16 bytes. And
How is this different? How is this more secure than
right, because from like the previous example, we don't have that chaining ability. So each one is kind of independently put from the rest. But because of this, the only thing that stands between the ciphertext and the plain text is the encryption. But now you take the output of the encryption each time and kind of build upon the previous one over and over. So this becomes a lot more random, which you'll see in one of the images. It's in one of the next slides.
And you only get access to the last ciphertext, or do you get access to each, like in this picture?
Well, each block is dependent on the last block, but it kind of recursively builds up, right? So the block, like
Like what would be the output known to the user?
the output known to the user is kind of like the, well, okay, the weakest one you could see is the first block, right? Because the
Like,
only
is that
thing
is the weakest one known to the user?
that's the weakest one known to the user. But the next two blocks are way harder to find than the other one. But all of the blocks together will make up the final ciphertext. You join them at the end, but you broke them into ciphers to be like specific blocks because AES only works at the block level. So you need to know all of the blocks to get the full ciphertext, right? So
So
You-
all these ciphertexts at the bottom are concatenated together.
yes, yes. That's that. Anyone else? All right.
Does that mean like stuff towards the beginning is like more insecure in a way?
Slightly so, but it all comes down to like how insecure AES is, which is already pretty hard if done right. So yeah, technically it is less secure because there's no like aggregation from previous
Yeah,
blocks.
I follow-up question. So let's say you know like part of the plain text and you have the output ciphertext. Can you recover the part of the IV from that, just from that first step? You said this AES is reversible. Well, I guess you don't know the key. There's two unknowns here.
Yeah, so
Okay.
that wouldn't be enough.
Okay.
But
You're
you'll see in the later examples, like the IV could be
The IV can be known to the attacker. Can still be secure.
well, if the IV is like known to the attacker, which in the industry, it's going to be like some random string of bytes that's only going to be appended, and the attacker would not necessarily like get it from those random bytes. But if the attacker like sees patterns in the ciphertext and is able to like get enough plaintext to be able to think that like the IV might have been null, then it might become a problem because XORing it with null doesn't really do anything. So there are cases where like the IV itself might not be very secure, and there are chosen IV attacks. But in practice, the IV is going to be sufficiently chosen to be safe
So,
enough.
like when you're decrypting this, you also need to know the IV, right?
Yes, which you could extract from like one of the blocks of ciphertext, the first one specifically.
So would it be reasonable to assume the IV is public since it needs to be known by both sides of the communication, like the encryptor and the decryptor?
Yeah, for, at least for this case.
So in this example, the only unknown to an attacker would be the key.
Yes,
All right.
which would be as hard as at, at least as hard or harder than 1/2 to the power of what the key like this, which is 128 bits.
Okay.
So that's a very hard problem. Yeah. So going a little bit back, this is actually going to create a key stream now from the IV and the key, which is again a randomly chosen like string. So the block cipher encryption, as we said, emulates pseudo-random behavior. So this is like the key stream being generated, and it gets fed in as like input into the next block cipher encryption with the key as well. So this kind of generates new key streams each time from each block, and it's XORed with the plain text at the very end to create the ciphertext. So this is kind of turning AES into a key stream in a way, but it's still a block cipher because the plain text themselves are depicted as blocks. So it's not really a true stream cipher, but it's supposed to emulate similar behavior to it.
So what's the advantage of this? You're just changing the order of operations with the XOR and encryption, right?
Kind of, yeah. So you're able to make it a little quicker than CBC because you're only passing in like an IV and a key through each round and then outputting it to like the key. So the plain text,
The size of bits going into the encryption are still the same length, right?
yeah, that's true.
I guess it's just more closer to a stream. Is this like widely used? I guess
Oh.
I don't know.
OB is somewhat used in SSL protocols.
Okay.
Yeah, they're all of the
Do
modes
you
are
know
used.
why that's good?
I mean, it finally depends on the scenario, right?
Right.
Even OFB has its cases where it might not be the best, and sometimes CFB might be better, which is a similar mode, except we take the ciphertext instead. I'll explain why they're different a little later. There
Like,
are
you know what an advantage of OFB would be
compared to what?
compared to the previous slide. Yeah.
CBC. Well, there are some attacks in CBC that would work, whereas in OFB they might not be as prevalent. I'll describe why a little later. Bear with me. It's taking some time. So again, why we kind of need modes. This was kind of like the picture I was foreshadowing for the ECB mode. And we could see when we kind of like take the Linux penguin and encrypt it in ECB mode, it returns like this pattern of it kind of returns this somewhat random pattern, but not really random because you could still like see the shape of the original image. And this makes ECB vulnerable to what we call a differential cryptanalysis attack, which I'll explain in another slide. But for other modes other than ECB, specifically this one on the right has been CBC encrypted because like each of like the blocks are actually chained together and you're not only dependent on the individual blocks themselves, it removes any trace of existing patterns that might have happened. So the result looks like a complete jumbled mess. So that's what you want. So how to kind of tell what mode's been used, specifically how to tell if something's ECB, which is generally considered the weakest encryption. If you see repeated bytes in the encryption, and if the ciphertext itself is a multiple of 16 bytes, that probably means that each block itself has been encrypted in an independent manner. Of course, this isn't enough because AES is still like a PRG, and it could have been totally random that they're the same. But if you have a plain text that's sufficiently large enough and you sufficiently see repeated bytes of data in different sections or different blocks, then that's a high clue that you might have been using ECB encryption. And if there's no sign of any repeated bytes, but the ciphertext is still a multiple length of 16 bytes, then because CBC and ECB doesn't actually like change the resulting like ciphertext output, then this means that CBC or ECB encryption has probably been used. And this is actually not the case in OFB because the ciphertext that like feeds out is like resultant on the key stream from before. So that's one difference between this and P. If you have a black box encryption oracle available, you could try sending 1 byte to the oracle. And if you get back 1 byte, this probably means that you've been using a stream mode, which is OFB or CFB. But if you get back 16 bytes, yeah.
So what do you exactly mean? I mean, I heard some classes, but what do you exactly mean by a black box encryption oracle? Is it just like a program which you feed data and it gives you the output?
Yes. So you don't have access to the internals necessarily. You only have access to whatever you gave in and whatever you gave out.
But the internal code is also publicly available, right? So
Well, you don't know what mode has been used though.
Ah.
The encryption protocol might be publicly
Okay.
known, but how would you know what mode has been used necessarily? That might not be known. So yeah, it's still a black box in the end. So if you get back 1 byte, that's probably been an OFB encryption, which is a stream-based protocol. Again, stream is byte to byte. But if you get back a whole 16 bytes, that means that there was padding involved. There have been like exact block to block encryptions. That means one of the whole block modes has been used, like CBC or ECB. So that's one way you're able to tell, which could be used in one of the challenges. Yes?
So even the stream modes still produce like a block of the key at a time. Like you can't actually produce wider kind.
I'm sorry?
So even the stream modes, you still produce like a block at a time of the key.
What do you mean of the key?
Like when you generate the key string, you don't actually generate it like a byte at a time.
Yes, yeah, you don't. Yeah, they're actually padded. But when you actually like put through like a single like block of data
Yeah.
of like a certain length, and you get like that block of data back as like a stream of data, that's probably mean like OFB has been used. But if you get like more than that, or like say you gave a plain text of like 17,
Yeah.
then it's gonna be a bit different. So
So like let's say you give it plain text of length 2 bytes. It cannot even in the stream mode, it cannot generate only 2 bytes of key.
no, it'll pad it back to 16. Anyways, where was I? Yeah. So differential cryptanalysis, if the cipher exhibits some sort of non-random behavior based on how the plain text bits change, and if you could trace some equivalent like information that's contained within the ciphertext, then it's likely that the implementation is suspect to differential attacks. So differentials in the context of AES are like the XOR values. So in the place that AES works in, XORs can be kind of considered like something that measures the difference because they only output 1 when the 2 bits are different at each point. So we could kind of consider them like difference machines in a way. So an example I kind of put here was if you have 2 known plain text blocks, P1 and P2, and you let the known XOR or difference between them be delta P, you could retrieve the corresponding enciphered blocks C1 and C2 and have the known difference be delta C, which is the XOR of the 2. So let the final round output be whatever like C1 prime is with K. That's what the output from the previous block, and C2 XORed with K prime. So C1 and C2 are the S box outputs. K is the round key. Those are specifically steps within the implementation of AES. So the delta C that we calculated, which is C1 XORed with C2, is actually directly correlated with C1 prime and C2 prime, which is a pattern that we've just seen. So an example where you were able to see this was the penguin from before, which kind of emulates like the shape, at least of the original penguin. That's somewhat like a way you could actually see this this formula there. Now, moving on to CBC, an example of an attack that I'm going to demo soon would be the bit flip attack. So the decryption formula that I said here was from the diagram was PI is equal to the decryption of the current block XORed with the previous block. So the current block is dependent on whatever came before. And the first cipher block is basically so each block of plaintext is XORed with the previous block of ciphertext before being encrypted. So if an attacker modifies a bit in the ciphertext of one of the blocks, then the corresponding bit in the decrypted plaintext of the next block will be flipped because that change will propagate over to the next block based on how we changed it together. So this could be useful for things like privileged escalation, which if you had a place where it's like admin is mapped to 1 or mapped to 0, then if you're able to get access to the ciphertext and change just one bit of that token and send it back, you could flip that bit within like that identifier to make yourself admin. So it's actually possible to use this for privilege escalation. Even OFB is pretty susceptible to the bit flip attack if not secured correctly. So a bit flip in the OFB mode will flip the bit in the corresponding plaintext. But a very important thing is that it will actually not clobber the current block you're working on. Because of how CBC is changed based on the previous block of text, if you flip a bit in the current block, the decryption will return a garbled mess for CBC, which sometimes you might not care about, but if somebody is looking at the other side and seeing a garbled mess as input in the system, that's a likely idea, like a likely scenario that the actual plaintext is not valid, and someone can be able to like go back and figure that something wrong has happened. Whereas for OFB, it's more silent because only the bit in the next block will be flipped, but the current block is still okay based on how they were changed together. So it's a lot more of a silent attack in OFB is kind of the idea that I was trying to go for. Now, the CFB mode, which is an alternate to OFB, will actually clobber the next block afterwards. So it's going to be able to be checked out and found out that a bit flip might have happened with like a message authentication code. So OFB bit flip attacks might be completely silent and they could be dangerous. Now, the last attack I'm really going to talk about in depth is the padding oracle. And the idea is that if a plaintext has been encrypted in CBC mode, you could kind of use the padding that's been known to use kind of a side channel attack. So if you have a padding oracle, which is like encryption that you could like pass something in, and then when it decrypts it, it will return whether or not like the resulting padding was invalid or not. So if you're able to modify an IV, the oracle can return to us whether or not the IV was actually accepted based on whether or not the ciphertext padding was valid. So going a little more in depth here. Yeah, I know I'm running out of time soon. Suppose you have cipher blocks C1 and C2, and you want to know what the second block's decryption is. And you know that public key encryption standard 7, PKCS 7 specifically, was used for padding. So PKCS, the idea is that once you have like a block of any length from like 0 to 15, then in order to pad it back to like 16 bytes, you basically, how am I going to explain this? I think I'll just in Zoom see. I'll just show it up here. So let's say you have something of like length 15 over here, then the end like byte that you have to pad will basically be 0x1, which is like the difference that's being used. And if you have something of length 14, then in order to pad it to 16, you need 2 bytes now. So instead, they're going to pad in 0x2, 0x02 at the very end, and so on and so forth, up until you get to like 1, which will pad 0x15 15 times to the very end. That's PKCS 7. But
And this is done to prevent like length extension attacks, right?
yes, yeah. So PKCS might not be the best padding standard because this looks pretty easy to tell what the length was from here. So there are other padding schemes that are known, and yes, they're specifically meant to prevent that. So the oracle tells us if the padding of the last block, no, sorry. If you flip the last byte of C1 to make C1 prime and send the IV C1 prime and C2 to the oracle can then tell you from decrypting the actual like sent message from the last block, and it's going to tell us if P2 prime was valid or not. And if the padding is correct, then we know that the last byte of P2 prime, which is the decryption of C2 XORed with C1 prime, is going to be 0x1. Let's say that, right? So after you found the last byte of P2, you can then find the second to last byte in a similar fashion by sending the last byte of P2 to 0x2. And you set the last byte of C1 to DK C2 XORed with 0x2. And you modify the second to last byte until the padding 0x2, 0x02 is actually returned. And you keep repeating this going backwards to reveal what the plaintext block is. So kind of had an image doing exactly that here. So let's say you don't know what the X is, right? And you want to find what X is. So if you have 0x3c XORed with X and you return as 0x01, you know that that's actually been valid. So by definition of XOR, you then go calculate what X is by doing 0x01 XORed with 0x3c. So that means that the plaintext byte there was 0x3d. So you just keep on XORing this byte with the corresponding byte from the ciphertext to get the plaintext byte at each location. So you kind of like continue this process now with 0x2x, 0x26 and 0x3c. And you kind of like continuously go backwards over and over again. And you can recover plaintext bytes that way through a padded oracle. That was kind of a lot. Does anyone have questions? Yes?
Can we defend against this attack?
Normally people don't use CBC anymore because of this. So the other encryption protocols, specifically OFB, is resistant to a padding oracle because of the fact that like you can't really propagate these kinds of errors back through previous blocks and have like the padding scheme known. So that's an example of why OFB is actually used over CFB, because you can't actually pad over OFB.
Why is the IV like so shit? Like why is it not all random?
Well,
All random bytes with the length. Yeah.
in practice, it normally is. In challenges, it would be a little difficult if it was random.
So in practice, it's more secure because of the random bytes.
Yes. Yeah. But in challenges, they're going to probably give you an easy like IV, like all nulls, for instance, is like a very classic IV that's used because that just kind of makes the first block easier to do.
So in this example, imagine you replace all the null bytes in the IV with random bytes. Can you still pull off this attack?
Maybe depending on like the exact bytes being used. Assuming that they are truly random, it'll be a lot harder to pull off the attack. But a lot of like the actual padding schemes being used are not that good in practice. Some of them are like maybe using PKCS7 in general, which if that padding might not be very good, then at least you've gained info about the length of the stuff that you have to look for, which might not be secure, even if the IV was very secure. So it's all like very scenario basic.
But I guess my question would be like, in the real world, is like this padding oracle attack, assuming the IV is random, is this a real legitimate concern? If you know.
Yeah, it did cause a couple of problems back in the past with SSL being susceptible to a padded oracle, even though the IV was pretty secure. So it was more of a fact of CBC being used rather than the other modes. So they switched over to OFB, which does not have this problem.
Because it encrypts the IV before it does.
Yes. Yeah. So there's that. It's a bit of a handful, but yeah. There are tools out there to actually automate this attack, and a couple of the ones below are Bletchley, Padbuster, which I used in one of the challenges here before. Padbuster is pretty good. There's another one that's been developed by researchers called Poet, and there's also Python padding oracle. So any of these tools you could actually use to automate the process. So you don't have to actually manually find and do everything all at once. So that's pretty good. And the general approach to these challenges are most of the CTF challenges you'll see have like a very specific attack scenario that's probably been discussed in a research paper. So if you look at the challenges and you're able to like see like what's going on, what have we missed, you're able to probably find a research paper that depicts an attack for it, and you just follow the attack from there. So that's the most common approach to crypto problems like this. There's also a crypto.stackexchange.com, which has a lot of good discussions about specific scenarios. SageMath is able to symbolically execute large cryptographic computations very efficiently. And I attached a document down there that explains a bit more of the internals of AES. So one of the challenges in our current set of challenges has to do with AES internals, and it's pretty difficult. So I'd highly suggest looking at that lecture. So a bit more on the next meetings. This Sunday, we'll cover Linux kernel exploitation with Max Bland, who's a PhD graduate recently. And he's gonna, again, talk about Linux strategies. And next Thursday, we're gonna have Anusha talk about AI hacking. Please come. We're gonna learn how to hack AI and I guess large language models. So that's gonna be cool. And next Sunday, we're gonna have a Japan House social. So come. It's gonna be fun. Yes, we love cherry blossoms. Yep. So that's all. Yeah.
How long did your demo take, Sagnik? Did you still want to do that, or?
I'm gonna do it. It's not too bad.
All right.
I'll show it.
Bye.
Assuming my computer opens. A little weird. What the hell? I'm restarting my computer because I think it froze.
I think the challenge is ECB.
ECB? Yes. In fact, the hardest challenge is ECB. The secret sauce one. But the one where you have to find like the ciphertext that is ECB,
I see.
I
Okay.
guess it not really an ECB challenge, but kinda.
Gotcha.
I just see.
Funnily enough, I made the beginner challenge one of the harder modes of encryption, which is CTR. But based on how it's used, it's pretty easy.
Okay.
But,
Yeah. So your parameter is called ID.
Oh.
Yeah.
okay, I'm back. I'm gonna do the demo very soon. I'm gonna try to join the Zoom meeting. Got it. I'm gonna attempt to share my screen real quick.
Only work by the same
Wait.
Does anyone see my screen? Wait, where's Min? Oh, Min.
That will embed it.
It'll embed it.
That's new.
It's for what? But the reason, like, so it only works with an inscription for the same repo.
I got my screen to share on Zoom, but I want to show it up there on the board.
Can you just drag it over? Where's the mouse?
That's my mouse, but this is Min's computer. Is he still on her computer?
Oh, you want to switch it to?
I think
I
he's
need
still.
to pull up the screen share on Min's and then. I don't know how they're dragging.
Yeah.
Oh,
I suppose.
let me make that one big.
I don't know what they don't do. Even if you erase the notes,
You're screen sharing?
Yeah, I'm screen.
You need
I
to,
tend to rebate
Just a second.
Yeah.
very often.
so you joined a Sagnik.
My work.
Yeah, I joined as my then screen shared over.
Well, it's probably good. Can you hit actually view?
Which one?
Just up here. View. Do standard view.
Standard or loose? I'll try standard. Eh,
You can do immersive, yeah.
I'm gonna try immersive.
Okay, never mind. Don't,
Oh,
don't do that.
that might not be
What's the
good.
other view?
Side by side view.
Side by side gallery and close out participants maybe. And then just close this out.
That's
Alright,
fine
let's close
enough.
it.
Close enough.
There's no force.
Does everyone see my screen and the Pokemon? Yeah,
But because
of course. Does everyone see the Pokemon on the terminal? Everyone's good? You see them on?
see them on. Oh. Did I still put the B up there? But
All right.
and push your changes to some.
Only one
Under four, so it doesn't have to like, and you now, like that brand is not valid. You don't want to rebase it for, you don't want your commits to be.
I'm gonna give it like 5 minutes, then I'll do the demo. But bear with me. I'm gonna make it fast.
Why 5 minutes?
I'm gonna take like 5 minutes for people to try them, then I'll do the demo. I'm gonna make it fast. It's not that long.
Introduce new
Trust me.
Keep a new commit, which is like change, so we can't just commit message, right? But if you want to like change the actual code, you have to do like a revert commit, which like, yeah, that works. Say you should do it for.
I'm gonna start the demo in like 5 minutes.
But if I'm using the PR,
You guys could try the demo.
until I close that PR, the state of mind, or until I like, mark it as ready to.
You can probably poll, see if anyone's working on a challenge.
Should be,
Because I think most people are just.
I assume.
I don't know if anyone's.
I still don't
give myself full
understand. Can you show me like a graph, like, because if you, even if you're on, so you're on a fork, right? You're editing things on the fork.
Yes.
Okay, and then where is the situation where there's something that is something from the origin or from the original?
Yeah, so imagine pushing. So imagine, okay, this is my fork, yeah. And then I have master,
Yeah.
and then I have a branch or PR.
Sure, yeah.
And so actually, I'm not gonna be but right now I have,
This is not secret, this is real stuff. They don't really. So when you're looking at nuances, this is more like. Yeah.
that's much like, this is Sage Darwin. And as you can see,
Master's there, yeah.
It's over there. That is, you can see this is actually not the same thing as
That's like.
our origin.
I did. These ones don't really.
I reordered the ordering and I had put the messages. I had fix me commit, which I changed by minutes.
Oh, is this so that the bits look nicer?
It's so that the bits look nicer. It's so I can make break cuts and not have to worry about it. Because like I want to be able to share my changes to the maintainers, but I don't want that to be.
Well,
You know, not to bust the.
I see, so you do need to rewrite history because.
You don't need to, but if I have something that works, or I think might work, it might
just
be
don't push.
tested.
What if you just did push?
How would I share my changes?
Oh, so you would share your changes, but then at the end, like
All right, guys.
preparing a final.
So I'm gonna demo one of the medium challenges. No, just kidding. I'm gonna demo secret sauce. Nah. Just kidding. Maybe not that
All
good.
of my commits.
But
yeah,
let's check out this one, right?
Hey guys, Sagnik's gonna do his demo.
Yep.
Guys, can maybe a little quiet, Sagnik's demo.
All right. So this is one of the medium challenges that I kind of whipped up in 30 minutes. I don't know how good this is, but I'm still gonna try to demo it. So welcome to SIGPwny. I made this very hard challenge, as you could see from the tag down here. So I made this so hard that if you're able to solve this problem, surely you're an admin, right? And we just connect via the port. So that's exactly what I'm gonna do here. As you can see, I've been kind of testing out the challenge, so it's in my terminal board, but let's go here. So welcome to SIGPwny. Ooh. Please log in. If you aren't already here, we will make an account for you. And how do you want to sign in? I don't really know what the hell the token is yet, so I'm just gonna say credentials. So let's see. Sagnik 3. This password I totally use everywhere else. I love crypto. Surely. All right, there's the token. So I don't know. I'm just gonna kind of copy that in. What happens now? I could probably log in as the same token. I'm just gonna try that out real quick. What happens if I decide to log in as token, right? Yep. Welcome to the club. Same message. So seems I'm able to actually log in. So I already downloaded the challenge. I haven't actually written the solution yet. So I'm just gonna open nvim real quick, go up to the challenge, and this is what the internal code looks like in the server. So over here, we kind of have our flag here as environments. So we could kind of see immediately off the bat here, we know the mode that's being used, and it's a CBC encryption, which you kind of remember is like the diagram that kind of like chains each of the blocks together from before, hence CBC, cipher block chaining. This AES block size here is always going to be 16. Very important to note. This is 16. So the decryption, we kind of strip out the IV and the encrypted data here, with data being up to 16. So that's the first 16 bytes. And then we have the rest of it after as like the blocks of encrypted data. Then we're gonna create like the cipher from the key that we just had. And we kind of built a very basic authentication system from this. So authenticating by credentials, that's kind of like the little game that we've just gone through at first. I'm going to take this is kind of like the flag that we have. It's going to check that the username is root and that the password is the flag, I guess. The user data here seems to be a JSON object, which is admin, and then seems to be a Boolean integer. So that probably means it's going to return some sort of JSON object, admin. I'm assuming because I didn't really log in as root anywhere, it's going to probably be 0 when I decrypt the token. So because we're able to set this to 0 and 1 at will, this leads me to see this is probably a bit flipping attack that we're probably going to have to use. But I'm just going to look at the rest of the function. Welcome to SIGPwny, blah, blah, blah. Okay, that's great and all. I'm going to go down to the solution down here. So I already have the trusty pwn tools. Always use pwn tools. They're very good for these challenges. Let's see. So from what I kind of did down there with the terminal, when I first encatted into the challenge, I was kind of here, and I wanted to first get the token before I log in, and then we need to change the token in a certain way to do the bit flip attack. So first, I'm just gonna make a function, get token, so that we're able to get our token. I don't really need any arguments.
Describe the bit flipping attack, maybe with the, like, what is a bit flipping attack?
Right, I'll get to that. Trust me. It doesn't seem to care what I take as credentials. Yeah, it doesn't actually care if I put any credentials in. So in order to isolate that block, I'm just going to make it very simple and define my username to be that and my password. That very simple. Why is it doing that? It's kind of weird. Anyway, I'm going to make my connection to the challenge. Very standard. It's going to be at port 1992. There's our connection. This is very annoying. It always indents weirdly. There we go. So I'm gonna then it seems to wait until it reaches this colon mark down here. So I'm just gonna do p dot receive until I'm gonna try to make this fast. I'm gonna send some line, and my choice is gonna be 1 because I want to go with credentials here, right? So I'm gonna again receive until it asks for the username and the password. I'm gonna receive until this, and then I'm gonna send my username and password. So I'm just gonna encode my username as bytes. E dot Yeah, I know I could have copied the line, but I'm kind of trying to do this from memory. Dot encode. I'm just gonna encode that. And then I'm just gonna receive one more time until the next colon. So I'm just gonna do that real quick. And then the token is this very last stretch of material down here. So that's at the very end. So that's gonna be token equals p dot receive line. That's that line with welcome, here is your token, and so on. So I'm going to take the last element, which is the actual token. That dot. So that gets us our token. We get to close and return token. Great. So that gets us the token. And now comes the actual part. Token equals bytes dot. Huh? That was unintended. Is going to get the token there. So that's the token we're actually going to receive from the server. And this is the part where the bit flip attack comes in. So the idea is that we could actually use XOR to kind of get the difference between what we want and the target that we have. So for people in person, I'm just going to kind of whiteboard that here very shortly. The actual bit flip attack comes from whatever you want to change. So that's admin over to 0. What's the difference here? Well, the target that we want is a very simple change. And that's going to be changing this guy to 1, right? So if we want to know the difference and the bit that we need to actually like select here, that's going to basically be the XOR difference between the two. So we at least know that part of the bit flip attack comes from XORing like the blocks that we want. Now, if you actually like see these sections, this is not exactly a block length of 6, which is very important. If we go back to the challenge that I have back over here, when we have admin and then we have like a space here, if I open character counter real quick and I type in this is 12 characters. So that exact like block of text that's going to happen is going to be padded. And because we didn't really pass in any padding arguments, the default for this PyCryptoDome module is going to be PKCS7 padding. That's something that you could actually like publicly find online. So the default is going to be PKCS7, which as I've shown before is going to always pad past the non-length. So because this is 12, it's going to pad with 4 of these to get to like 16. So this is actually the block that we're creating. And then one more exit 4. And the same thing carries on down here. So this is going to be our original. This is going to be our target over here. We're going to try to XOR them together to see the exact like bit that we need to change. So when I do that down here, that's just going to be I'm first going to find the IV because the IV is going to be needed to actually decrypt. And that's just taken in a similar way to the encryption from before up to length 16. And then blocks is going to be the rest of it. So that's everything that comes after. Now the original that I just stated from before, that's just going to be at the byte level. That's going to be the admin 0, and that's going to be padded with 4 of these. Yeah. And then the target is just that's just going to change to a 1. It's the same thing. So that's the single bit that we flip. And we're going to then change the IV that we actually send because the first block of text is just going to be this exactly. So the final bit flip attack we're going to do is going to call in the XOR method from Pwn tools, and we're going to pass in IV and then reg targ all XOR together. And token is going to be equal to. So this part actually does the attack. because this kind of like finds the exact bit that we need to change in that first block, which this is the first block because I specifically didn't give a username and password before. So this is the block that we need to change. And the first block for CVC is going to be the IV. So the original like 16 bytes that we've gotten so far is going to be our new IV. So this XOR will make the change in the actual target. So we're going to then take the original blocks of data there and turn it into hex because we need to send byte outputs. And then we're going to do and then we're going to need to find a way to send the token, which I forgot to write. So just going to create something called send token. Bear with me, guys. I'm almost done. Probably going to do a p dot. Just copy all of this from before. So that's going to set up the challenge. There's stupid space there every time. So what happens when I try to like log in as a token, right? If I try to log in as a token, this is kind of what happens there. So in that case, it's going to probably ask for what token I want. So I'm just going to do a p dot receive until, just going to return until there. So it's going to enter my choice. So now I want to log in as a token now that I've gotten the token that I just changed. So I'm going to send the line 2 to log in as the token. I'm going to then p dot receive until. So this is going to wait until I get to enter my login token right now. So that's going to be at the byte level. Again, this guy, p dot send line token dot encode, because we're passing in hex into there. And then p dot receive line. And this is because in the challenge, when we actually like are admin, and we have admin, it's going to put some line here that's kind of there before it actually prints out the flag. So I'm just gonna skip past that line by doing a receive line. And then I'm gonna do, I want to print out the line that actually gives me the flag. So I'm gonna do p.clean.decode to show it as actual text, p.close to close it out. So after that, I'm just gonna do a send token of the changed token. So this should work, I think. I'm kind of doing this from memory, so I hope it works. Python 3 sol.py. What do you know? It worked. What do you know? Yeah. So I think the main idea behind the bit flip is you need to know exactly which block you're in and which bit that you want to flip.
Can you scroll down to the code where you do that calculation?
Yeah. So that's just this part down here with the XOR. Now the XOR is, again, a difference machine. It's able to output 1 in the exact locations that the bit is different. And the bit I want to flip is from a 0 over to a 1. So if I'm able to XOR target and rig together, along with the first block, because I didn't have any like username here in the first position, I know for a fact that this must take up the first block. So that's the first block of the token that we had down here, over here. So whatever 16, this is probably not of length 16 that I'm highlighting, but whatever this is down here is basically the corresponding ciphertext of the block. And because this is CBC encryption, we know that there's nothing standing in the way between the decryption and the first block of text. If this was in the corresponding second block, then the first block would be garbled, which could be a problem sometimes, but the bit flip attack could still work in the second block if the message in the first block is not authenticated or not checked. So even if it was a garbled mess as a result of the decryption, if that's not checked out, it could work, but it's not as reliable. So because of the fact that we didn't give a username and a password in, the first block had nothing standing in the way. So we were able to directly change the first 16 bytes, which we assigned up here, XOR it with the difference that we just calculated. So that's the whole bit flip attack. And the result is pretty much almost going to be the same as this first 16 bytes, but some of this data in the middle is going to change as a result of the decryption. But the result is that this block like bit is actually going to change because of
Flipping, it's like bit in the initialization vector.
the flip a bit in the plain text. Exactly. So that's kind of a chosen ciphertext attack is what we'd actually call it. But this over here is the entire attack. It's pretty short. But the other thing that was very helpful to know was that if I go back to challenge.py,
Why is that the first 16 bytes of the token?
I just gave it the name. The IV is what's XORed with it really. But
really just the first.
It's the first block. I could have called this block, I guess. This is kind of a misnomer, but yeah, it's the first 16 bytes because I know that this is going to be the first block because I didn't give it any username or password. Specifically, that part is when I go up here. I was able to figure out that I could send empty stuff. So yeah, it's pretty cool, huh? Yeah.
Cool.
Yeah.
Sorry.
Of course. That was a little long, guys. Sorry about that. I tried making it short from last year, but there's so much. Stop recording. Where? Oh. It's up here. Yes.